let us now go back to the basics for a moment. Recall the combinatorial interpretation of the binomial coefficients. So what does it say again? It says the following. Let n be a non-negative integer and k a real number. Let S be an n-element set. Then the number of k-element subsets of S is n choose k. Can we prove this bijectively or by double counting? Well, not really, because n choose k was defined as a fraction. A fraction per se doesn't have a combinatorial meaning. It wasn't even obvious that that fraction is an integer. However, we can write this out as a fraction, and we can move the denominator on the left-hand side, and then we can see if we can prove this bijectively. So let me spell this out. First of all, without loss of generality, we assume that k is a non-negative integer, since otherwise our claim is just saying that 0 equals 0. In that case, there are no such subsets, and this is 0 as well. So that's not a very interesting case. Now, if k is a non-negative integer, the definition of binomial coefficients says that n choose k is n minus 1, n minus 2, ... n minus k plus 1 over k factorial. And actually, we learned a name for the numerator. We learned to call it n lower factorial k. So this is like an exponent, but with an underscore. And let me just recall the definition. This is defined to be this product. This is called the lower factorial of n and k, or falling factorial is another way. And if you look at this closely, k factorial is k minus 1, ... 1. So this is also the same as k underscore k. This is also a lower factorial. So we must prove that this fraction, that the number of k-element subsets is this fraction. Equivalently, we must prove that this number times the denominator of the fraction is the numerator of the fraction. And this equation has no division in it, just products and, well, products, basically. So it looks like we could be proving it bijectively, or at least we could try. So let us recall what this lower factorial means combinatorially. In theorem 2.4.4 of lecture 16, we proved that the number of injective maps from an m-element set A to an n-element set B is n lower factorial m. Okay, so we want k instead of m, so we just replace it. And we also we have an n-element subset, namely S, so we don't need to introduce a new subset B. Now we also need a k-element subset A, so let me just define this, and I'm going to call it k. So this is a k-element subset consisting of the first k positive integers, and by the theorem from lecture 16, the number of injective maps from k to S is n lower factorial k. All right, so let us count this number in in another way. We already counted it once, and we got n lower factorial k. Now let's count it again and get the left-hand side. So we do double counting, basically. So to obtain a double counting proof. So to that purpose, we recall the notion of the range of a map. If f from x to y is any map, then the range of f is defined to be, this is denoted by im f. This is simply the set of all values of the map. So basically all values of f. Thus, in particular, for any map f from k to s, the range So by the way, the notation im stands for image. This is another way to say range. So the range, aka image. People also say ren of f, but this also means other things. So this range, this range is a subset of S then. Moreover, if the map F is injective, then this range im F is a k-element subset of S. Indeed, if F is injective, then the values of F are distinct. This is what injective means. An injective map sends distinct elements to distinct values. But these values, what are these values? These values are f of 1, f of 2 to the dot f of k. So f has k distinct values. But this means that the set im f, which is the set of all values, has k elements. Okay, so any injective map f from k to s has a range im f that is a k-element subset of S. Thus, by the sum rule, instead of directly counting the injective maps from K to S, we can count them according to the range. And this range is going to be a k-element subset of S. Okay, now, is it any easier to count this? It turns out that yes, because what is an injective map from K to S whose range is R? It is basically a bijective map from K to R. Let me try to explain this on a picture. Mathematically, it's not much harder to prove this formally. So let's say this is K. And let's also say this is S. And let's have an injective map. Where are the arrows in Zoom again? Here, I guess. Nope, these are the wrong arrows. So, yeah. So a map is injective. In that case, it looks a bit like this. Notice that no two arrows hit the same point. So if its range is R, let's say the range is this little circle, except I don't want it to be green anymore. So this will be R. Then I can forget about all the elements that are not in the range because they're not taken as values. And what I have is an injective map from K to R. But this map is not just injective, it's also surjective because R is the range. So every element of R is a value by definition. I've restricted the target set to only those elements that actually are taken as values. So the map has become surjective and it's still injective. So it's bijective. So restricting an injective map, I get a bijective map. And conversely, of course, if I have a bijective map from K to R, it's an injective map from K to S whose range is R. So since an injective map from K to S whose range is R is essentially the same as the bijective map from K to R. And when I say essentially, I'm just paying respect to like the pedantic notion of a map from K to S being not the same as a map from K to R. But this is really not a difference we need to pay attention to. Okay, what do we know about bijective maps from K to R? We know that they're the same as injective maps from K to R by the pigeonhole principle. How can the pigeonhole principle be applied? So first of all, which one? The one for injections. The sets K and R have the same size because R is a K-element set, but K is also a K-element set. So the sets have the same size, so any injection between them is it's a bijection by the pigeonhole principle. And therefore, the bijective maps are the same as the injective maps. And now we are on familiar ground. We are counting injective maps, which we know how to do. It is a lower factorial, again, by theorem 244 in lecture 16. But now it's k lower factorial k, because both of the sets have k elements. So it's not just a lower factorial, it's a regular factorial, in fact. So we are in this familiar situation where we have a sum, but all the addends are equal. So the sum is simply the number of k element subsets of S times the addend. Okay, and now we're done. We have computed this number in two ways. In one way, we got n lower factorial k. In the other, we got number of k element subsets of S times k lower factorial k. And if we compare them, we get the fact that they're equal, which is exactly what we wanted to prove. So comparing these two results, we find that they're equal. As explained above, this proves the theorem. This is actually how the theorem is often proved in textbooks. As a reminder, we proved it using Pascal's recurrence because it was conceptually easier. We didn't have to think about injective maps and pigeonholes, but really this proof explains how exactly counting k-element subsets gives you this fraction. This is the number of ways to injectively map the first k positive integers into the subset. And this is the number of ways to map the first k positive integers on a given k element subset of that set.